Och nu börjar konferensen lila mot sitt slut och sist ut har vi ingen mindre än Chris Klug. Och Chris är utvecklare på Active Solutions och beroende på vem man frågar så kan man säga att Chris antingen skapar eller löser problem. Han älskar att bygga och skapa saker. Applikationer, ett nytt kök eller en radiostyrd helikopter. Och Chris bygger saker mest hela tiden. Men för det mesta betyder det att han skriver kod och löser kunders problem. Och ett ämne som länge legat Chris varmt om hjärtat är solid-principerna. Och det är principer han idag kommer att ifrågasätta. Häng med nu, för nu kör vi!
So, hi everyone. I guess I'm the last session of the day, so it's kind of I'm the only thing between you and dinner by now, but hopefully I'll make it worth your while to actually sit around and listen to me talk. So I'm going to talk about the not so solid principles. That's the name of my talk, which is a bit weird, but I'll get an explanation to it in a little while. As mentioned, my name is Chris Klug. I work as a developer / architect / basically anything you pay me to do for a company called Active Solution in Stockholm, where we do software development in different areas for different clients. But I've been talking about the solid principle for quite a while, and actually I Googled it because I just realized I've talked about it for a long time. So this is actually my session for the solid principle talk at TechEd 2014, which is where I think was my first time I actually talked about it. So I've been doing it for a long time, and I've started sort of looking at the principles and questioning it, if it's actually the right way to go, and if there are some weird things going on that we might want to consider now that the principles are getting old. So today's talk is the not so solid principles, where I will start kind of picking away at the principles to have a look at, are they useful today? Are they actually worth looking at, or have we moved past them with the software that we're building today? But before I get started, I want to look at this thing here called principle. So what is actually principle? Well, I Googled it, and I got the definition of it. And there's a lot of text here, but it's basically a fundamental truth or proposition, blah, blah, blah. But the interesting part is this. So for the option 1 here, it says a fundamental truth. I'm not 100% sure that I would consider these principles to be any form of fundamental truth. They're not that deep, to be perfectly honest. And the other option here says a scientific theorem or law that has numerous special applications across blah, blah, blah. Really, they're not quite at the level of a scientific theorem or law. So honestly, I would question calling them principles to begin with, but that's more of a semantic thing. But I just want to mention that because I know that that's been talked about a little bit before. But let's go ahead and have a look at the solid principle one at a time and see what they a bit of what they mean and why I'm looking at them with a bit of questioning today. So the first one we've got is single responsibility, and single responsibility principle is all about, your class should have a single responsibility, which often turns down to or boils down to this thing of saying a class should have only one reason to change. And that's a good statement, right? It's going to have one reason to change, and if we only have one reason that can affect it and one reason that can change it, we're unlikely to change the code, and we're unlikely to introduce issues because we're making changes ever so often to the code. The problem with boiling it down to this, a class should have only one reason to change for me, is what is the reason? So there are lots of different views of what single responsibility actually means, but my main problem with it is actually that there are so many different views of what single responsibility means. What is a single responsibility, or what is a single reason, and so on. So somebody said this, or boil it down to only one requirement should be able to cause a change to a class. And basically, it boils it down to saying it's a requirement. So the reason to change, the reason part becomes a requirement, which is really neat because if we have really big documents of requirements for all of our code, we can sort of boil them down and look at different classes and say, so this requirement here will cause this change and this requirement here will cause this change, which is neat and cool. However, I might be alone, but I don't think I am. in feeling that we don't generally start building software when we have a fully spec'd out requirements list with every single requirement up front. We tend to start working before the requirements are completely clear, which makes this a little bit complicated. To make it even more complicated, Uncle Bob came out and had another definition of it. He says, and he's actually the founder of Solid, he says a module should be responsible to one and only one actor. And here it becomes down to an actor. Now we're talking people. So now all of a sudden the class should only have one person that's responsible for the code. So basically one person's choices or wishes for changes should be the thing that changes it, which is kind of interesting. I saw somebody mention that sort of like, oh, there should only be one C-level person allowed to have sort of impact on your code, and if there's more than two people involved making decisions for your code, it should be split. So now we're talking people. Now it's not requirements, it's all of a sudden people. And then just for the heck of it, I actually went, and Uncle Bob also wrote this little quote here on Twitter, which is another way to think of SRP, single responsibility principle, is gathering together things that change for the same reasons and at the same times separate things that change for different reasons or at different times. That makes sense. It's a bit more pragmatic. What catches me with that tweet is one word. I don't know if you can see this, but he says reasons. That's plural. So first he comes out and says we should have single responsibility, there should be a single reason, and so on, and all of a sudden there are now multiple reasons and to make changes. So single responsibility becomes a bit muddled. But single responsibility principle is not the only thing that talks about this concept of having clear definition or semi-clear definitions of how to build your code so that you don't end up changing the same code over and over and over again and having to have sort of like a single responsibility. In the pragmatic programmer, it says, we want to design components that are self-contained, independent, and with a single well-defined purpose. That sounds to me very, very close to what you are wanting to achieve with single responsibility. It's actually very close in my mind to that principle. However, the pragmatic programmer is not talking about single responsibility in this case. The pragmatic programmer is actually talking about cohesion. And I don't want to, so the idea of the single responsibility principle is good, but I think what we're aiming for is actually having high cohesion. We want to make sure that our classes are cohesive. Everything that has to do with one thing ends up in one class, which means that it's going to be a small enough class that we know what it does. It's very specific in what it does, which means that it's only going to change when that specific feature of your application changes. And I think that is what we're aiming for, but I personally believe saying that we want to aim for high cohesion is better than sort of single responsibility principle. And also, we do want to add low coupling to that. It's another one of these old ones. You should aim for high cohesion, low coupling. So yeah, there's nothing wrong with what we're saying with the principle, but to me, my conclusion when it comes to single responsibility is, yes, I think we should aim for high cohesion and keep our classes highly focused on doing one thing really, really well. But I do believe the single responsibility principle as such is too blurry and too unfocused on defining what it actually means so that it's hard for people to understand it. So I would say high cohesion is better than saying single responsibility. The next principle is the open-close principle. And open-close principle is the one that, after all these years of presenting, it's been the one that I've had the hardest time actually presenting and talking about. And it's mostly because it's actually felt a little bit wrong from day one to explain it. I don't know why, it just has been like that. And the principle as such says software entities should be open for extension but closed for modification. And that kind of makes sense in the way that, okay, if we don't change our code, we don't change it, we don't do any modifications, we're not likely to introduce problems to it, but we should still be able to extend it. And that's where it comes sort of, what does that actually mean? Well, actually, if you boil this down, it comes down to, if you need changes, you need to inherit your class and add stuff to that class. And okay, makes sense, because if we don't change the original class, We don't introduce bugs in existing code that we know it works. We're just extending it and adding new things on top of it, and that's where we might introduce new bugs, but we're not going to do it in things we already know works, which is a good idea, definitely. But we need to back up a little bit before we talk about this principle, or when we talk about this principle. So this is the guy who came up with it. This is Bertrand Meyer. Bertrand Meyer is a French academic, consultant, author, and he's also the creator of Eiffel. So the reason that I brought up creator of Eiffel, which is a programming language, is that it's actually quite important for open-close principle. So in Eiffel, adding fields or functions to a library inevitably requires changes to any programs depending on that library. Here's the important part. Requires changes to any programs depending on that library. So basically, in Eiffel, if you build a class and you distribute that class to different clients, if you ever add a function or a property to that class, you're actually changing it, and it means that any client depending on it will have to be rebuilt. And that means that for Bertrand Meyer, the solution to this was, let's never change a class when we need to add more features to it or extend it. Instead, let's take that class, inherit it, do a new class, and then clients using our library can either depend on the old version, and they don't need to be recompiled or rebuilt, or they can pick up the new inherited version, which then means that they would have to be recompiled, but they would have to do that anyway because they're using new features. So that makes a lot of sense from Eiffel, but it doesn't make sense from the code that we're doing today. C# doesn't have that limitation. Few languages, if any languages today, have that limitation if you're using a modern language. And also, to be perfectly honest, the principle is a versioning issue. It's not a software problem. The problem is that they couldn't version Eiffel stuff in a good way, Eiffel code, which meant that when you did a change, it caused problems to the clients. If you'd had proper versioning and version management, clients could just have kept going with the old version, and then you could have released a new version with more features, and it would have worked even if it was the same class name or the same class. So honestly, it's more of a versioning problem than it is a principle for software development in my mind. And then you have that question, but what about polymorphic open-close principle? So first of all, we have to explain what polymorphic open-close principle is, I assume, and that's basically the idea that we base our classes off an abstract base class or an interface instead. And by doing that, we have no functionality that we have to adhere to. We don't have to inherit any functionality like you would in Meyer's version of OpenClose, because you would inherit the class with its functionality and then you would extend it. In this case, we have no functionality to inherit because it's empty, or we have an interface that defines the things that we need to implement. So that actually brings us up. So what's the difference between Meyer and polymorphic? Well, Meyer says you have a base class, you have some implementation, you have some functionality, you know it works, you have deployed it to clients, you inherit that class, you add more functions to it and more properties to it, and then you deploy that, and then clients can use that. So basically, you inherit the implementation, but you change the interface. Polymorphic goes and says, let's have no implementation and have a fixed interface instead, which is literally the opposite of what Meyer was talking about. Meyer says, have functionality, change interface. Polymorphic says, have no functionality, no changes to the interface. They're two completely separate things, so actually they're opposites of each other. And it's just always been weird for me to explain, and also open-close feels weird when it comes to interfaces and abstract classes because it's hard to explain how to do it properly. So honestly, when it comes to open-close, original limitation is gone. We don't have that limitation anymore. We're not building, well, actually, some of you might be building in Eiffel, but I assume that you're not. And if you're not in Eiffel, what I expect from this conference doing C#, or at least VB or some other .NET-based thing, or any other modern programming language, we have version management in place today, so that's not a problem. Ignore it. Together with open-close, we get Liskov substitution principle. Liskov's substitution principle is awesome. That's the one that I would place closest to this whole theorem law thingy that I had as a principle to begin with, because this is actually, it's defined as this. It is defined as let Qx be a property provable about objects x of type t, then Qy should be provable for objects of y of type s, where s is a subtype of t. This makes all sense in the world. To some people, not me. But the main thing with this is that it probably doesn't say what you think it says. Because I personally find that we have taken that and we have bastardized it into a version that fits into software development in the way that we want it to fit in. So let's have a look at the actual quote here, or the actual outline of what it says. And look at the first part here. That basically says anything you want to have that you can prove out of Qx, so basically any property that you can prove out of x, which is basically out of a type t, that, and if we look at the second part here, then that desired thing should be possible to prove for object y if that's basically based on a type that inherits from t. Which basically means that anything you want, anything you like to have in the base class should be possible to prove in the inherited type as well. So pretty much not what we're saying when we're talking about Liskovs, because we're basically saying, oh, if you can call a method on this class, on the base class, you should be able to call the same method on the subtype. But the thing is, this actually goes deeper and says we can prove what comes back and such things. So anything, basically anything we desire from the base class should be the same in the inherited class, which brings us back to a lot of what Meyer said, that we should make sure to have a base class and then we inherit and we add more stuff to it. So the previous conditions of what we expect from the class should still be there, but there could be new features on top of it. That's not what we're saying when we're talking about Liskovs. We're saying, as I said, oh, we can have this method, but we can change completely what it does. Well, that's not really what she's saying. There are also a couple of rules combined with Liskovs. So rule 1 and 2 is that we should have contravariance of method arguments in a subclass and covariance of return types in a subclass. So what does that mean? Well, what it means is any incoming parameter, or any method rather, should be able to take a more specific version of the input arguments than was defined in the base class. So if your base class expects car as an input, you could go and say in the inherited subtype, you can go and change that and say, I want sports car. And that would just work, because as long as they become interchangeable, because as long as you push in sports car, that would be fine. And the other way around is that covariance of return types in the subclass means that you can return something more specific than what was returned from the base class. So basically, we read in that, oh, that's fine. That means that we can accept more specific things. We can accept less specific things in the command argument. Sorry, not more specific, less specific, but we can return more specific. That sounds good because it allows us to basically change our types. But honestly, in C#, VB, most other languages, you can't change the signature. The signature of your method is always going to be the same when you inherit it. You can't change type. So let's just skip rule 1 and 2 because you can't actually fail on those. Rule 3, no new exception types are allowed to be thrown unless they're subtypes of previously used ones. This is a good one. This is actually quite useful because what we're saying is don't throw new exception types when you inherit the class, because if you throw new exceptions, existing code that's out there that knows what the base class was throwing might have try-catch around it, catching specific exceptions. If you start throwing new ones, then you might break existing code. Nothing wrong with this principle. Keep that in mind. Rule 4. Preconditions cannot be strengthened in the subtype and postconditions cannot be weakened in the subtype. Basically says you're not allowed to add more requirements in your subtype. So you can't make changes to the code in a way that you cannot call this method unless you have done this before, if that wasn't a requirement in the subclass, in the base class. And also post conditions cannot be weakened, which means that you cannot inherit it and make changes so that things that you could do to the previous class you can't do in the new one. So it's a matter of keeping your class to a point where anything you could do in the base class, you have to be able to do in the inherited type. And anything you couldn't do in the base class, you are not allowed to do in the inherited type either. So basically, don't change anything, because you're not allowed to change what you can use in the class. Makes sense. Also very limiting, because all of a sudden, why would I need to inherit things and make changes? Yeah, there are a whole lot of questions that this opens up, but it's another one of those, sounds good on paper, but I don't think it fits very well into our software development paradigm, to be perfectly honest. And then the last rule is the so-called history constraint that says if a class is immutable, sorry, hard to find that word, immutable, you're not allowed to make it mutable when you inherit it. And if it's mutable, you're not allowed to make it immutable, which kind of fits into the preconditions and postconditions situation of not strengthening or weakening. So once again, if it wasn't possible to write to the value in the base class, you shouldn't be able to do it in the new one. And if you were allowed to write to it, you're not allowed to change it so that you can't write to it. So basically, don't change your class. You don't change any of the provable things about the existing class, because it could break stuff. There's a good comment about this on Wikipedia that says it's a semantic rather than merely syntactic relationship, because it intends to guarantee semantic interoperability types in a hierarchy. Actually, Liskov is more semantic. It's not about being able to substitute class A with class B because they have the same interface. It is more of a semantic thing of how they work and deeper things than just the API corresponding to the previous API that you had before. So basically, the conclusion here is, doesn't mean what you think it means. Having that said, once again, when we boil it down to bastardized version that we are using, it kind of, there's nothing wrong with it, and we could keep using those ideas, but it's not quite what they're saying with it, with the Liskov substitution principle. The next one is interface segregation principle, and this is the one that's the easiest to talk about, because it basically says clients should not be forced to depend upon interfaces they don't use. So the idea here is that if you have a big class with a lot of functions on it and properties, and you put that into one big interface, it means that first of all, you're sending way too much functionality into any classes depending on that interface, because they don't need all of that. And secondly, implementing a huge interface with lots of methods and properties on it is actually quite annoying and complicated, and you sort of go, oh, do I really want to do this? By breaking the interface down to smaller pieces, it's easier for us to do sort of more scalpel, precise incisions and go and say, I'm going to change this little part of my application for this new implementation, instead of I'm going to go and change this massive thing in my new application. There's a big problem with this when it comes to solid principles. The big problem here is that if you have aimed for single responsibility principle, or high cohesion, as I told you to do, instead of specifically single responsibility principle, then this wouldn't be a problem, would it? Because if you aim for a highly cohesive class that does one thing, or maybe two or three closely coupled things, really, really, really well, you're not going to end up with 50 methods and 270 properties. You're going to end up with small, precise classes, and you're probably, with really high cohesion, you're likely to want to switch out the whole implementation and not just parts of it, which you would end up doing if you had a massive class, which would require a big interface. So you're unlikely to end up with all of these big interfaces if you have done high cohesion properly. Unless it is a part of business requirements. It could definitely be in a way where you look at your domain and you realize that, oh, there's a business requirement for me to break this down into smaller pieces. There has to be specific rules around writes or deletes or whatever. So we want to put writes and deletes in a separate interface because the requirements from the business are like that. That's a different story. You're allowed to make small interfaces to support your business use case and break interfaces into smaller pieces. But keep it like that if you're doing business requirement things, not because, oh, I have a massive class that has too big an interface. If you have that, go back to the start, rewind my presentation, look at the single responsibility part, and then start over again. So basically, once again here, aim for high cohesion, just as with single responsibility principle, and you're not going to have this problem of huge interfaces that need to be implemented, which means interface segregation principle kind of goes out the door because it's just not there. Which puts us at the last principle. The last principle is dependency inversion principle. And dependency inversion principle is actually quite good. I like the dependency inversion principle. I know that the talk before me, Sergey was talking about dependency injection in .NET Core and ASP.NET Core. It solves a bunch of things, and we're getting used to it a lot. However, there's a difference between dependency injection and dependency inversion. The one is a technical thing, the other thing is for lack of a better word, a principle. So the principle says high-level modules should not depend on low-level modules. Both should depend upon abstractions, and abstractions should not depend upon details. Details should depend upon abstractions. What does this actually mean? Well, it means that we should use concrete types and specific types as little as possible. As soon as you take a dependency on a specific type, you have a dependency on a specific type. You can never change it out. And as soon as you do an interface, for example, that depends on a specific type, once again, you're locked in with that forever. So basically, you end up with this situation where what the principle is saying is object A should not be forced to depend on object C just because it depends on object B. Okay, lots of letters here, A, B, and C. But if we look at it here, what we're saying is that as soon as you depend on a specific type, then you end up in trouble. Because what happens here is that if object A takes a dependency on object B, basically object A goes and instantiates B, and then B goes and instantiates C, then you end up with this annoying chain where actually object A doesn't only become dependent on object B, it also gets dependent on object C. So by having B depend on a specific, you're forcing the class above to also depend on that specific version. So what we want to do is we want to make sure that we don't depend on specifics, and instead we open it up so that we can tell a class what to depend on. So it would look like this instead. So if object A instantiated object B, but instead of B taking a dependency, or rather newing up object C, it defines an abstraction and says, I need something that implements this interface, or this abstract base class potentially. Then object A can go and say, oh, I have an implementation for you, I'm going to inject it into you so you can use it. That way, object B gets the dependency it wants, however in an abstract fashion, and object A only takes a dependency on object B and can then choose to take a dependency on object C, or maybe D or E or F, or whatever dependency it wants to take. But it's up to the consumer to define what dependencies I want. It shouldn't be forced by the child class to define what dependency it should have. So I would say dependency inversion is awesome. However, it's also getting to a point where we're doing potentially a little bit too much with it, because it does add a lot of complexity. It does, in most cases, mean that we have to implement the IOC container. We need to start doing dependency injection. We need to invert everything. And I'm torn here because a part of me loves that a lot, but a part of me is a bit annoyed that we might be taking it too far, because adding this thing here, if we don't need it, is just an extra layer of complexity that we need to keep in mind and that we need to figure out. And when you do dependency inversion and you use an IOC container and you do dependency injection, then the problem with that is that you don't know what classes are going to be in your application and what hierarchies you're going to have until you actually run the application, which adds yet another problem in there. How do we know what's configured, what's working together, and so on? Which is just a bit complicated. And especially, an interesting point here is that we add abstractions on things, not just because we expect them to change in the future, to be perfectly honest. I would dare to go and say that probably at least 50% of the abstractions we build in our applications on a daily basis are not there because we want to switch out, in this case, C, for our application's business purpose. Instead, I would say that probably 50% or more have this dependency inversion feature for completely different reasons. They have that because I wanted to be able to unit test it. So to be able to unit test it, I need to be able to inject my mocks or my test stuff instead, and so on and so on. And although I agree with that, I do believe that that's a pretty good idea. Once again, you're coming back to complexity because your running application will now have all of these abstractions and injections and IOC frameworks that creates things on the fly as your application is building and so on. When all we really want is a fixed implementation, we know it's not going to change, but because we want to run our unit tests, we do go ahead and do this. And I'm torn, to be perfectly honest. I get the point of doing it. I get the point of the unit tests. I get the point that we have to do it to get unit tests to work. But I also believe that we might be doing it a bit too much and adding a bit too much complexity with the whole because that's the way that we do it kind of thing. So when it comes to dependency inversion, I think we're looking at, yes, I would keep using it, especially because it's it's good, but it's also built into ASP.NET Core and .NET Core in a high way. So basically with .NET Core, it's there. And if it's there, we might as well use it. It was hard. It's more of a complicated thing when you had to implement your own stuff and add your own IOC containers and all of that. But I also do want to sort of take a step back and say, but beware of the complexity. Beware of the fact that you're adding a layer of abstraction. You're adding things in between. It makes it harder to read. It makes it harder to follow the code. It makes it harder to do a lot of things in your code, to be perfectly honest. And that's something we should keep in mind. And I'm not saying skip doing it because it adds complexity. I'm just saying take a step back and sort of have a look at, do we really need this complexity, and does this complexity give us anything in return? Because if you start adding complexity not because it gives you anything back in return, just because the complexity is supposed to be there, you might want to have a look at something else. So generally, I would say the solid principles, if you start going really deep into them and you start looking at what they actually mean and you start digging into listgovs and you realize that listgovs work with data stuff and data manipulation, and that the listgov principle came out of something different than what we're using it for, or open close principle coming out of Eiffel actually having a versioning limitation and things like that, then it becomes a bit muddy and so on. But if you skip diving deep into it and you just look at the surface and you look at the kind of cute interpretations that we software developers have done to these principles to make them fit into the software paradigm, there's stuff to take away. There's definitely knowledge there that's good to use, and there's definitely thoughts behind it. But I do believe that there might be other things we want to focus on today, where tooling has helped us a lot. We've got new languages that help us a lot, and so on. So solid principles, not bad, but it needs a bit of sort of caution of what I actually do with it. And you don't want to dig too deep, because that just ends up with me, which is I have a problem with them because I have read more about them and realized that they don't quite fit in. But the initial version of it was quite nice. In 2014, I loved them. In 2014, I would travel the world and talk about them because they were the best things since sliced bread. And now things change. Have a look at other things. One suggestion would be look at Dan North. He has the idea of Cupid. I think Kevlin Henney has one called Fluid. They have other acronyms with other principles that they find better in today's software development that I would recommend having a look at instead of Solid, potentially. Other than that, I just want to thank you. I'm sorry for delaying your dinner, potentially. I hope you got something out of it. If you have any questions, I think I might be getting a question or two. Yes, it seems like I will be getting a question. If you have any questions you didn't want to put up right now, I'm available on Twitter. Just go ahead and ping me there, and I will see if I can get you an answer. Thank you so much.
Thank you so much for that, Chris.
Thank you.
And yes, we have some questions for you. So the first one is, you have been teaching Solid for several years. What are the most important principles, if any, to follow to make software robust?
The most important principle is not one of the solid principles, but it sort of fits in there. If I have to choose a solid principle, I do believe that the single responsibility is probably the most important one. But as I said in the talk, I would rather turn it into high cohesion, because high cohesion solves a bunch of other problems. So that would be my preference if I had to choose one.
Yeah, yes. I think you talked a little bit about this, but it's my understanding that the solid principle has been widely accepted for many years. But do you see a shift in the industry now towards something else?
I'm seeing a shift, yes. I'm seeing a lot of questioning of the principles. I'm not seeing a specific shift into we should do this instead. I'm just seeing a questioning mantra of, it's old and so on. And I don't agree with the whole, because it's old, we shouldn't use it. It's kind of, I've been involved in projects where people have said, we're going to do this, and I've said, no, we can't do it like that. We've tried that before years ago. Oh, this is JavaScript, it's going to work now. Doesn't work like that. There's still certain truths in software that's going to be there however long you wait anyway. But so the argument, it's getting old, we have to switch because of that? No. The principles have issues? Yes. Look at other things. And yes, there is a move away from it. Unfortunately, I feel like the move might actually be it's too old. And that's why we need to move away from it.
Yeah. Okay. Thank you so much.
Thank you.